Welcome everybody. I'm Zhilong Huan, I'm a postdoc here, and today we are very glad to have Dr. Jose Martinez-Lorenzo to come here to give us a talk about the subsurface sensing and the imaging at speed using information in 4D and field acoustic, electromagnetic, and acoustic seismic wavefields. So let me first introduce Dr. Martinez-Lorenzo, and he is assistant professor at Northeastern University, and he acts as the director of the Sensing, Imaging, Control, and Actuation Laboratory, and he holds a joint appointment in the Department of Mechanical and Industrial Engineering and Electrical and Computer Engineering. So his talk is about speed and fast, but his research interest is quite wide, and I cannot just use a very few words to introduce his research. So typically his research interest is focused on high capacity sensing and imaging systems with a lot of application, for example, on the move of security threats, biomechanical, and also geophysics. And he received the 2017 NSF Early CAREER Award for the research program entitled 4D millimeters wave compressive sensing and imaging at 1,000 volumetric frames per second sensing and machine learning. And he had several four best papers awards in conference with over like 1,200 papers. And his work has been featured by CNN, NBC, New York Times, and World Magazine. Okay, so let's welcome our today's speaker, Dr. Martinez-Lorenzo, for his talk. Thank you very much. Go ahead.
Thank you, Tom, for inviting me to this seminar. It's really a pleasure for me to be here. I'm going to be around here so I can point and see you all. As you well said, the title of the presentation is about how can you do imaging faster, and how can you do more accurate reconstruction by fusing different imaging modalities. So I'm the last person here because this work has been done by my students and former students, and so they deserve most of the credit, if not all, of what I'm going to be presenting today. Okay, so let's see if this works. So the idea is that there is a deep need in order to try to understand what is the interaction of different type of physical fields with the fluid flow and the transport in the porous media. So as you know, there is a lot of physical processes that happen at different spatial and temporal scales, and we don't fully understand everything nowadays. So the idea is, okay, if we can somehow couple the information from different orthogonal sensors, are we going to be able to do better predictions in the physical and dynamical events that are happening on the subsurface? And that's what we are trying to address in our lab by developing this system that combines three different type of waves: electromagnetic waves, elastic waves, but also thermoelastic waves that are the coupling of the electromagnetic waves and mechanical waves through a thermodynamic process. And the ultimate goal is that if you have the information from the different wave fields, you should be able to better model and characterize the interaction of the fluid flow in the porous media. So if you think about what is the holy grail that we are trying to find, is that Current subsurface exploration is relatively slow because you need to drill the borehole, you need to put the antennas, move it at different positions for multiple transmitters, multiple receivers. So that's in general slow in terms of deployment and the recollection of those antennas. Most of the cases, the imaging is slow. Because you're using large amount of data in order to reconstruct the subsurface properties. And also, since there is not a deep understanding of the different coupling that might happen between different physical fields in the porous media, sometimes you have a lot of artifacts that might result in expensive decisions in terms of what to do next. And the other thing is that most of these systems, they are not adaptive. They do not take into consideration what do we know as a function of time regarding the area that we want to do the imaging. So what is the holy grail that we're looking for? How about if we were able to actually do a fast deployment? Instead of having a full array of transmitting antennas and receiving antennas, we only have a few of them. And if we only have a few of them, maybe the deployment is faster, and probably you don't even need to do the recollection of those sensors. And also, if those sensors are particularly tailored to measure different physical fields, we might be able to do a better imaging or characterization of the different underground processes that might be happening, and actually we can get some type of quantitative imaging, reconstruct what are the petrophysical and constitutive properties of the subsurface. And finally, if we can actually leave those sensors there because they are so cheap to deploy, maybe we will be able to do imaging faster and over larger time scales and adapt to what are the processes happening there and what is the actual dynamics of the subsurface, and be able to do imaging in an adaptive fashion. So this is somehow like the holy grail. Of course we are not there, but we are trying to get as close as possible. So what is our approach? Well, our approach, as I said, is we're going to be fusing different wave fields. Then we are going to bring the principles of information theory into the sensing process, which, to the best of my knowledge, that's not something that has been done often in the past. And by using these principles in information theory, we are going to be able to design these systems that we call systems with high sensing capacity. And the idea is that they can transfer a larger amount of information per unit of time between sensors and the imaging domain. So, what is the overall program that we are building in the lab? Well, the idea is, okay, let's assume that we're going to model the subsurface by a set of petrophysical properties, which is the mixture composition of the different materials, the soil, the gas, the water, and also the rock or the matrix. And the idea is that we're going to try to reconstruct those petrophysical properties in the imaging domain by fusing the information from different sensors. What are those sensors? Well, electromagnetics, acoustics or seismics, and then the thermoacoustics. The idea is that if we can produce these rock physics models for the acoustics that transform these petrophysical properties into the constitutive properties of the acoustics and seismics, or the constitutive properties of the thermoacoustics, or the constitutive properties of the electromagnetics, then we should be able to do the full wave inversion not in this high dimensional space where they might have or propose different solutions, but we do the inversion in this joint space which reduces the dimensionality of the problem. And then what we are going to try to do is to apply some of the fast solvers that can be executed in clusters in a parallel fashion, and because of that, we can do a fast reconstruction of all those spectrophysical properties on the subsurface. And then, of course, we can try to do some coupling with some fluid dynamics as well. So this is somehow like the whole perspective of the subsurface sensing and imaging program that we are building in the lab, which we are building that for Department of Energy Geoscience program. So today I'm going to focus mostly in this branch, in the thermoacoustic imaging, because I think it's the most novel one. Most of you probably know a lot about the acoustic or seismics and about electromagnetic. So let's focus a little bit more on what is this coupling of electromagnetic and mechanical waves through this thermodynamic process. So the idea of using thermoacoustic or thermoelastic imaging for subsurface imaging was extracted from its use in biomedical applications. So the idea of these thermoelastic waves is that you have given targets that you are radiating certain energy into that target. So what happens is that diffusion time is very slow compared to the temporal poles through which you are producing that energy. So therefore there is a volumetric expansion, and that volumetric expansion produces an acoustic wave or an elastic wave which is propagating outwards. So once again, you deposit the energy with electromagnetic fields, and then you produce the mechanical wave that you can measure at a distance. And the idea is that with this process, you can get information about some of the constitutive properties, the electromagnetic constitutive properties, in particular the conductivity, as well as some of the thermodynamic process, constitutive properties like the heat capacity and volumetric dilation of that particular target. And you have better resolution than if you were to use only one single modality. So, as I said, in the past it was used to image the biological media, but it has not been explored into the geophysical imaging applications. And that's somehow what we are trying to do. So the second thing is that if we want to be able to image fast processes in the subsurface, we need to be able to collect all the information we need in a short amount of time, right? So if you think about traditional sensing and imaging mechanisms, normally one way to do this very cheap, if you think in terms of the thermoacoustic excitation, is that you have a certain radiation, this target goes through volumetric dilation, and then you have here your transducer that you move at the different times in order to do the imaging. So this is very slow if you were to image there a process that is happening fast. Another way you could do it is just have the transducer in a fixed location and then in a fixed location, and just do some mechanical rotation of the sample, and you should be able to do imaging as well. But once again, that takes a lot of time to collect the data. So an expensive, even more expensive solution would be if you have a limited amount of resources, just put all the transducers in the particular position, and you can do that fast, okay? But that's expensive, and that collects a lot of data, and once you collect the data, where do you save it, okay? So is there a way in which we can collect only the information that we really need in order to do the imaging? And the idea is that, yes, you can do that if you now think about the sensing and imaging process from the information theory perspective in 4 dimensions. So the idea is that we can use certain artificial structures that have the ability to maximize information transfer efficiency between certain sensors and the imaging domain. And in particular, in our case, we are using these Holey cavity and acoustic metamaterials in order to enhance that information transfer efficiency. And the idea is as follows. So if you have here two sensors, so two transducers that are receiving the fields, what we can have is enclose that through this artificial structure that is producing some resonant modes that is giving you information about the targets from different directions at the same time. So is the idea of coding the wave field that you are producing to illuminate the scene in 4 dimensions. Those are the same principles that they are using, let's say, in video compression. Video compression, you only transmit some of the pixels of the image, but those pixels, they convey enough information such that you can reconstruct the whole image as whole. So this is something similar, is that we're going to produce some kind of pseudo-random illumination that will enable us to collect more information in less amount of time. And then, in addition to do this volumetric coding in 4th dimension, then we can start applying some smart imaging algorithms that leverages on the dimensionality of the object that you're trying to reconstruct in order to do the imaging. So let me show you a quick summary of this volumetric coding. Let's say if you have these point sources and you want to do imaging of a particular target, what you can do is to put this artificial structure that is going to produce different codes in the imaging domain when you scan as a function of frequency. The whole idea is that this system can be considered to be a high sensing capacity system because it can transfer more information per unit of time into the imaging domain, from the sensors to the imaging domain. And the interesting thing is that this information or capacity of the system is going to depend on these complex wave propagations from the transmitters into the imaging domain. But it's also going to depend on the uncertainty level. And that is a very important concept that I will emphasize slightly later. So if you want to read a little bit more on what is the math behind this information theory for coding that can be used for communications, for imaging, when you have multiple transmitters, multiple receivers, and so on, you can read this paper. It will be published soon, but it's already available in arXiv. And the idea is the following, is that when you have that, let me see. Okay, so the idea is that instead of illuminating with the spherical wavefront, what we are doing is producing these pseudo-random patterns that is producing an illumination of the scene that contains, if you think in terms of plane waves, more plane waves. But since you know these patterns for let's say, a homogeneous media without the target there, you can leverage on this information of these plane waves that goes from different directions in order to extract more information per unit of time. So let's think about what is information. What is information? So if we need to think about information, then we need to go and talk about the Kolmogorov and Tikhonov concepts of epsilon coverage, epsilon entropy, and epsilon capacity of sets in functional spaces. So what's the meaning of that? Well, the meaning is the following. Let's say that I have a volumetric area that is a source region. And I want to transfer information through a wave from this source region to this observation region. And my goal is to be able to determine what is the maximum amount of information that I can transfer from this region into that region. Well, the interesting thing about forward wave propagators is that in general, they are compact operators and they have analytical kernels when the observation and the source domain are not collocated. What that means is that this functional can be discretized into a matrix where there is a finite number of modes that you can excite in this region that can be transferred into that region. So what are those modes? Well, the modes are the following. If you get the functional operator that propagates a wave from this source domain into this observation domain, and you discretize that, and you compute the Hilbert-Smith decomposition of that matrix, or the singular value decomposition of that matrix, the number of modes that you're going to have there, it depends on the number of the singular values that you have in that discretization of your forward model. But not only that, it also depends on the energy that you allocate to that particular singular value, or left and right eigen or singular vectors. But only those who are above a certain uncertainty level. And that's the concept of information. You need to account for where is the uncertainty level that you have. And the interesting thing about this is that now you can compute the entropy that you have associated with that forward propagator and measure how many bits you can transfer from this source domain into this observation domain. And that's a quantitative value, okay, that is measured in bits. So what is our goal? Our goal is, okay, if I have m degrees of freedom that I can put in that source domain, and m degrees of freedom I will have in this observation domain, if I were to put a single source in each one of those ellipsoids, I will get enough degrees of freedom to transfer all the energy, and I will get the highest achievable capacity of that channel. However, what I want to do is, I don't want to put a source in each one of those ellipsoids. I want to use a few of them. And I want to reach a capacity that is as close, or an information range that is as close as that of the free wave propagating from source to the observation. So, just choose how do you excite the fields in this region such that you excite the highest amount of modes that are above the uncertainty level. And that's the concept of coding that we are going to describe now. The idea of coding is as follows. And you can think this about, because this comes from the communication theory, you can think of a communication theory and an imaging system as sharing very similar concepts. The idea is that in a communication system, you have a particular message that is unknown. What you want to do is you want to apply some type of temporal code to that signal that you want to transfer to this receiver. And the idea about this four-dimensional coding is that that message, you can do some temporal coding, but in addition to that, you can modify the surroundings of that signal that is transmitted by applying this type of volumetrical coding. I can put artificial structures that produce a scattering that is actually performing this type of coding of the wave field that leaves my sensor. So this is the concept of coding that you can apply in communications. Then you have a propagation matrix, let's say through the complex media, and I might have an object there that in this case, I don't know this object. Actually, in communications, you know this object because you have, let's say, direct view from the transmitter and the receivers. Then you have other free space propagation, and then in the receiver side, you might have also a structure that is also reassigning the energy from the volumetric space, and then you can also apply some temporal coding in the reception. So this is how you do a communication system. How do you do a sensing systems? Well, in the sensing systems, you know what is the message. And you can choose what are the temporal and spatial codes that you want to apply, such that when those codes illuminate this unknown object, the amount of information that you can extract when you have this receiver on that side also propagating through the free space, the number of singular values that are above the noise level is increased when you compare that with the case where you are not doing the volumetric coding. Let me show you a little bit more clear here. I think that is going to be easier to understand. If I say, well, if you remember when I was computing the capacity, I used this full matrix that I said for this volumetric region, you put one source in each one of those ellipsoids. This is the maximum capacity that you can transmit. But now I have a compressed matrix, which that means is that I only excite with a few of those antennas. So what I want to do with this matrix, where I only excite with few antennas, is I want to design what is my temporal code and my volumetric code in the source region, as well as my volumetric code in the receiver and temporal code in the receiver, such that the amount of energy that I receive is, or the number of singular values that I receive above the noise level is increased when you compare that with the non-coded version, okay? So the idea is that these sigma m, these are not singular values, of course, is just account for the amount of information that, or amount of energy that you couple to the mth singular value of the free space propagation. And same here, that this sigma ARR is just the amount, or accounts for the coupling between the mth singular value in the free space and the energy received through that in the receiving channel. So just to give you more broad idea is that you have a signal here that might have different pulses as a function of time and different frequency. So we can do a shared coding where as a function of time, we allocate the energy for different frequencies at different directions. We could do this type of punch coding that what this is doing, that in the time or in the frequency domain, I introduce a null. So I have two packets entering at all these frequencies, and I just drop that one. We can do smash coding, that is a device that gets the energy in space, in this case x and y, at different frequencies, and combine all of them to put it in a single packet. And then you can do this 3D coding in which packets for a given period of time with different frequencies allocate the energy into different frequencies in a volumetric space in a pseudo-random fashion. So this is the idea of the coding. So let's going back to the thermoacoustic problem. And how are we doing the coding? Well, in our case, we're going to put this cavity on top of the target region. And we are only use a limited number of transmitter or receivers in order to be able to do the imaging of this target. So let's see first what is the physics that we need to use in order to account for or model this thermoelastic wave propagation. So the idea is that we are going to have waveguides in the bottom of this structure. Here there is a coupling fluid. And what we are going to do is we are going to excite with an electromagnetic wave this imaging region. Then what is going to happen is that electromagnetic field that we solve with a full forward model based on Maxwell's equation is going to produce a field in this imaging region which is going to deposit energy in the location of the targets. So how is that energy deposition working? Well, in order to do that, you need to go into the heat equation. So basically what happened is that the electromagnetic field, it can be seen as a source that is depositing energy that is going to depend on the conductivity that you have at that position, as well as the electric field, and it also depends on the temporal pulse that you are using to excite the electromagnetic wave. The other interesting thing is that you are going to have a term that is going to account for the coupling of the energy into the mechanical wave. So if you think about this pulse excitation, in our particular case, we're going to use short pulses between 3 or 4 microseconds. And the way it works is that we radiate with the electromagnetic wave. And when you have a target with different conductivity than the background media, what happens is that you are going to deposit energy. Diffusion time is much larger than the duration of the pulse. And as a result, what is going to happen, there's going to be a volumetric dilation or constriction, depending on the case, which will produce a thermal wave propagating outwards. So if you think about what's happening in terms of the electromagnetic wave excitation, what we are doing is at the beginning, we do not radiate energy. Then we radiate with our microwave source a very strong signal with high power, but for a short amount of time. Once again, the diffusion time, if you think in terms of the temperature, is too slow. It will take much more time to diffuse than what is the actual duration of the pulse. And what is going to happen then, when you stop the pulse, what is going to happen is there's going to be another coupling of the part of the mechanical wave that was being stored is going to be given back to the energy, to the temporal wave. And that's going to start to propagating as a joint wave that couples the mechanical wave, the temperature wave, and also the mechanical wave. So how is that coupling happening? Well, if you think in terms of the solid mechanics, pretty much you have the stress tensor that itself depends on the elastic strain through the compliance matrix. And that elastic strain is going to be the total strain, and we need to subtract the inelastic strain. And the inelastic strain is part of this thermal strain that is proportional to the thermal expansion, as well as the change in the temperature that you have. So if you look at now what happened with the pressure that you will produce, you can see that there is the deposition of the thermal wave, and then there is a stress that is propagating outwards. So there are certain simplifications that you can do if you want to solve this problem using just a very simple wave equation. And the way you do that is by applying the acoustic approximation. So in this particular case, instead of computing all the solid mechanics also in the area of the receivers, we just impose the boundary conditions to couple the mechanical wave into pressure wave, because this is going to be actually our liquid, and this is the wave propagating through this cavity, and these are the openings. Okay, so this is the interesting phenomenon that I really like it, in the sense that, okay, when you radiate the electromagnetic energy, and you can see that the pressure is building up as a way as the thermal wave. I don't know, the scale might not be clear, but do you see the wave propagating outwards as well? Yes? So this is interesting because both this thermal wave and the pressure wave are propagating at the same speed. So if you look at what are the pressure and the temperature at these particular positions, what you can see is that actually, as a function of time, once you apply what is the electromagnetic pulse, the temperature is going to rise, and then the pressure is going to be coupled as well to this temperature, to this thermal wave, and then is the coupling between the pressure and temperature that is producing this wave propagation mode that is propagation outwards. So it's a very interesting thing to see that they are coupled and they are traveling at the same speed, which is nice. So this is somehow like the wave propagation that you will be observing for the targets. And as you can see, there is a very pseudo-random patterns that are produced in the cavity. And there are certain delays, and therefore there is additional information that we can extract from that complex scattering derived from this cavity. So how do we do the imaging? Well, the inverse problem, we need to start from the full wave modeling, which is the microwave. Microwave energy will deposit energy as a new heat source, as we were saying. So this is the coupling of the energy that is coupled into the mechanical wave. And then we also account for the amount of temperature, the mechanical wave that is coupled into the heat wave. But if we're going to do the imaging based only on the pressure that we measure, we can leverage on the acoustic wave equation, where we have certain inhomogeneity regarding the density there. So where is that coming from? The first thing is that if you look at the heat equation, and basically you just you neglect what would be the coupling of the energy or the heat source into the mechanical wave, you can see that the temperature pretty much raises and produce this flat excitation after you discontinue the energy. So once you do that, you can apply the solid mechanics to acoustics approximation that is well known and you all know. And then what we can do is just couple what is the volumetric dilation and the bulk modulus. And once you couple that, you get a relationship that tells you what is the temporal variation of the pressure that relates the heat source, the heat capacity, volumetric dilation, and the propagation speed. So if you now consider the sources who has the same dimensions as this second partial derivative of the pressure over the wave speed, you can see that this is acting as a new source. And then you get to the thermoacoustic imaging expression, in which now your source for the pressure, it depends on the heat source, that is depends on the electromagnetic excitation, volumetric dilation, as well as the heat capacity. So if you think about what are the actual effects of doing this approximation, on the left is what are the pressure waves when you use the solid mechanics, fully solving the tensorial form, versus the acoustic approximation, which is in the first reflection in this particular area is a good approximation. Then you can, in order to do the imaging, we did that by working in the frequency domain, and then you get to, and then neglecting for the imaging region what is the density terms, if you already can account for all of these known area. But here in the imaging region, we are just not going to include what is the density variations in this particular form. So at the end, you get a linearized system where you have the pressure as a function of the frequency. You have some Green's functions that propagates the field from any source location to an observation location. And you have the source term that is frequency dependent, and that's located at the source region. And the amplitude of the source is going to be proportional to the volumetric dilation, heat capacity, as well as the heat source. And remember, the heat source depends on the conductivity of the electromagnetic, conductivity there. So let's see a little bit on how do we compute the Green's function. So we're going to use the reciprocity theorem. And in order to do that, we are using the actually density and homogeneity inside of these parentheses before we apply the del operator. And what you can see is that for a source that we locate here, you're going to have this pseudo-random pattern. So the way we're going to do it is for each position of each transmitter or receiver, we are going to excite what is the pressure distribution in the imaging domain, and then we are going to use that as our background Green's function, that is considering the inhomogeneity of the cavity, but is considering the imaging region to be homogeneous as a first approximation. So once you do that, you get an equation like this, where we have this approximation of the Green's function by this background that, once again, accounts for this complex, this non-homogeneous media, that is the cavity. And then if we want to make the imaging independent of the electromagnetic pulse that you are exciting, you can just deconvolve the exciting pulse from the pressure that you measure. So as a result, you get a linear system of equation that is of this form. And the idea is that we only want to use now a limited number of receivers. So what is this linear system of equations giving us? Well, this is the following. So we have a set of measurements based on the pressure. We have this matrix that is derived from the Green's function approximation that we derive for the whole cavity structure. And this is the source term that we want to do the imaging with that. So the idea is that if we want to use a limited number of receivers, this matrix is clearly underdetermined. Okay? So how do we solve this? Well, in our particular case, we are interested in solutions that are variations or small variations to a known background. Okay? So what we can think is that the solution that we are looking for is somehow sparse for a given dictionary of basis functions. So when you do that, what you can do is solve for the norm zero, or in other words, the sparsest solution vector that still satisfies your data term fit. And you could even add, actually this is not correct. This shouldn't be this regularizer there. Sorry, there's a mistake in that slide. It's going to be corrected in the next one. I'm gonna describe that later. So when I'm saying here that this is sparse, okay, so the solution that you're looking for is minimizing the norm zero subject to these data constraints. So forget about that. That's a mistake.
X is a wave field?
Sorry?
X is the wave field?
X is the source term that is giving us the information about the volumetric dilation, the heat capacity for every point in the imaging domain. And this is the somehow like the wave propagation from any of the points in the imaging domain and the sensors that you measure. So you might say, well, but where do you get these sparse solutions that you are looking for? Well, if you think about time-lapse imaging, okay, let's assume that for somehow I already spend a lot of resources to get this background solution, and I want to do a temporal analyze how is the temporal evolution of this particular point. Okay, so if you look at the difference between the two of them, there is only a few pixels that are going to change their value. So this is clearly a sparse solution. So this compressive sensing approach, in which we try to find the sparsest solution in the imaging region, they happen very often in time-lapse type of applications. So let me describe now, this is the right formulation. And the idea is that what we want to do is we want to minimize what is the data misfit subject to that this solution that you are looking for to be sparse, and to be sparse you can enforce that by solving the norm 1 instead of the norm 0 when this matrix A satisfies certain mathematical properties, that is the restricted isometry property. We can also include certain regularizers in terms of the energy of the solution that you are looking for. And the way we solve this is by using this alternating direction method of multipliers, in which first you can solve for one part of the function that you are optimizing, then you can solve for the other part of the regularizer, and in their iterative fashion you make that the two solutions converge to the same value. So if we want to solve in a distributed fashion this type of problems, which involve norm 1 and norm 2 minimizations, they can take a long time. So the way we do it is by using this consensus-based alternating direction method of multipliers. And the way it works is that if you have your linear system of equations, what you can do is you can break your matrix into blocks. So each one of those blocks is going to be solved in one core in a cluster. Once you do that, what there is going to happen is that each one of the blocks is going to propose a particular solution. And what you need to do is what is called the consensus, in which the solutions that you are achieved by each one of the blocks, they converge to a similar result. And that's the way we do it in this particular case. So we divide this into blocks, so you get the solution for each block. And what you are making sure is that at the end, in what we call the consensus step, the solution provided by each one of the blocks is the same as the one that you are looking for. You can go into more of the details there's more papers, but that's somehow like the basic idea. So now if we think about, once again, these Green's functions that you might be observing for a point source, you get this circular phase front. And here, for the cavity, you can see these pseudo-random patterns that are being produced that are providing information from more plane waves. And as a result, what you are doing is by measuring the field here, you get information from different directions with the single measurement. So if you think about information, and information is just how many different signals you can measure or distinguish or tell apart from each other, this structure has the ability to give you more information. So we can also see these effects if we look at what is the pressure field that you will measure there. Once you excite with the electromagnetic wave, you have volumetric dilation, and then you measure what is the field there. So here's the electromagnetic wave, and here is in dashed line is what you would measure if you have no cavity. Okay, so it's pretty flat. So you just get this direct path somehow from going from this point to that point. Probably you have a little bit on the back, maybe is somehow like the interaction from the back and so on. But you can see that most of the information content is in that position. However, when you use the cavity, now you start having less energy in that position, but then you start having echoes. Okay? And those echoes are perfectly defined by what is the Green's function of this Holey cavity. And as a result, you are going to be able to extract information all along that trace and not only in this period of time. And once again, here you can see what are the fields when you do not have the cavity. But here when you have the cavity, you can see all this reverberation going after, happening afterwards that is going to provide this additional amount of information that you need. So what is the results that you can get when you apply this Holey cavity? Well, you can impose on sparse solutions, and you can impose on energy solutions based on the alternating direction method of multipliers formulation that we described. And as you can see, when you impose the sparsest solution, not only you can localize the target, but you can start seeing the actual top and bottom reflection of those particular targets, which is very interesting in terms of resolution. So now, here is the interesting point that I want to make about this information theory in 4 dimensions. If you look at the singular value spectrum of that matrix that is actually sampling the imaging domain, what you're going to see is that without the cavity, your singular values decay very fast. Okay? So if you have a signal-to-noise ratio that is about 20 dBs, when you don't have the cavity, you're only going to have about 40 singular values or modes that you can use in order to do the imaging. However, when you have the cavity, and if you have the same signal-to-noise ratio, you can see that now you can do imaging with a larger number of singular values, which in this case is like 80, and therefore you're going to be able to do a better imaging. Okay? Using exactly the same number of receivers and the same bandwidth and the same particular characteristics of the excitation sources. So this is very interesting in the sense that, of course, this is normalized. So the truth of the matter is that this is not 0 dBs, but this is going to be about, let's say, minus 10 dBs. But still, the amount of singular values that you are going to have for this signal-to-noise ratio is going to provide you more singular values that you can use to do the imaging. However, if your signal-to-noise ratio is too low, let's say 5 dBs, and this curve, if you don't normalize, starts here, then don't apply this type of coding because you will get more singular values over the noise level when you don't do the coding. So that's why it's so important to be able to measure what is the signal-to-noise ratio when you are doing this high sensing capacity imaging. Is there any other particular ways in which we can do this wavefield coding? Yes, and it is with this metamaterial. The idea of a metamaterial is just artificial structures that are made of aluminum, rubber, and steel that presents a particular dynamic that makes that for a certain excitation source, you get a strong absorption or transmission behavior. So if you have an acoustic wave that goes in this direction, there is a particular frequency in which there is a deep reflection or transmission, if you want to think it in terms of transmission and reflection. And the interesting thing is that if you look at what would be the density that you can extract from this particular material, you have an effective negative density behavior. And if you think about the bulk modules, you can also get a negative bulk modules at those resonant frequencies. So that's what they call metamaterials, because negative density of negative bulk modules is not something that you will find in normal materials. So we have done the design of instead of having the cavity, we can have different metamaterials that resonate at different frequencies, and that is helping us to have different illumination patterns for different frequencies. And as a result, you can also increase, I don't have it here, the resolution of the system, and actually this should be saturated. But what I want you to see is that you have these pseudo-random patterns that you produce when you put here these multi-resonant metamaterials going from the source to the imaging domain. So let's see some experiments, and I'm sorry if I'm going too fast or because time is almost done. But basically, how do we create these thermoacoustic signals? Well, we have a function generator, a microwave source generator. This is a very strong high power amplifier, it's 4 kilowatts, and we produce a 1 microsecond pulse with a 100 hertz repetition rate. So that energy is coupled through a wave guide that couples through an oil bath into the imaging domain. Then we have the target, and right now we are not using the volumetric coding, we are just moving our transducer linearly. We haven't produced our cavity yet to show you some of those results. Then the pressure wave is excited, then is amplifier. We present those in an oscilloscope, and everything needs to be synchronized. So there is another interesting phenomenon, that is that instead of using a pulse, we use a frequency modulating source. And when you produce a frequency modulating source, what happens is that you're going to produce very interesting results in terms of the thermoacoustic wave. So remember, instead of a pulse, it's just a continuous wave variation. We have the same amplifier and the same type of experiment with the same data collection and the same display. So here is the pulse excitation, and you can see what is the thermal wave propagating. And this is the FMCW. And what you can see, and I'm sorry if the contrast is not very good, is that here there is going to excite somehow like a higher frequency modes, and it's going to have a depression in energy there. So let me show you this better. So if you think about the pulse version of the thermoacoustic wave, you have the signal that propagates forward. Now with the frequency modulated, so now our pulse is about 30 microseconds, so you transmit through here, but within the pulse you have a frequency that is increasing. So what this is doing is building the energy in what is the material. When you stop the pulse, you have this depression in terms of the pressure that you are produced. And the interesting thing is that the amplitude of the pressure wave that you create is larger with this FMCW signal than with this pulse pressure. The other thing that I want to mention is that it seems like you are capable of keeping the energy from going into a diffusion state when you start using this FMCW. So let's see what happens when we go into the lab and we start measuring these things. So here is our source, here's our microwave amplifier, this is the microwave source, this is the ultrasound receiver, this is the scope, and this is the scanner system, okay? So if we look on the side, right now we have here a target, okay, which is just a highly saturated target. Actually, it's a piece of chicken. Here is a waveguide, and the waveguide is producing the electromagnetic radiation there. Here we have an ultrasound transducer that is receiving the pressure wave that is produced by this chicken. And let me show you from the top. What we are doing, here is the chicken, as you can see, the chicken breast is highly saturated. It's all in an oil bath. And what we are doing is we are moving the transducer down so we can get multiple views of the scatter pressure produced by that particular highly saturated structure. So if you think about what is the signal that we measure when there is no chicken or there is no organic material highly saturated, is something like this. When we put the object in the imaging region, we start observing those pressure waves arriving to the transducer. And this is very nice because this is our measured pressure versus our simulated pressure with the mechanism that I showed you before. Is not the same, of course. Simulations are never exactly the same as the experiments, but in this case even worse because our simulation is basically in 2D, and as you can see, that results were in 3D. But still, I think that we captured what is very well what is the nature of the wave excited by this particular structure. And is this model that we use to simulate the pressure that we are using to compute the Green's function at this particular medium. So, yes?
Can you comment or show in the picture the geometry of this particular pair of waveforms? And in particular, what's
this one?
Well, the top slide.
The top slide.
You have a blue curve and a dotted red curve. At the beginning, you have a very large pulse that appears to be saturating some capacitor.
This one?
Yeah. Mm-hmm. And I want to know what's the geometry of that acquisition. Is there a source? Is there a receiver?
Yes. So here is the electromagnetic source radiating from the bottom. It is this is a waveguide. It's very big. Okay, let me go to
Where's the receiver?
Here's the waveguide. Okay. So what is happening is that we excite the electromagnetic wave upwards. Here is the target, and this is the transducer. I don't know if you see the metallic part. Do you see the metallic part there? It's a circular transducer over there.
And it's a hydrophone, it's an ultrasonic.
Yes, it's an ultrasonic
And that
receiver.
pulse is the strong EM pulse interacting
Exactly.
with the
So
recorder?
that first pulse that you see here, that first pulse that you see here, this one, is actually the volumetric, because the electromagnetic wave, you see, this is very strong, and we hypothesize that this energy is already also dilating what is the constitutive properties of the ultrasound itself, because it's very close to the electromagnetic source. So that is also going to go through a volumetric dilation. That's our hypothesis for this one, because, you know, here's where the pulse is happening, and this is the pressure that we measure. So if we measure this pressure, the wave from the chicken did not have enough time to travel to the receiver.
And you're going to show us an array of measurements that combines what happens when the receivers move.
That's correct.
Okay.
That's correct. Sorry for if I wasn't very clear on that. And this is what is our prediction. And of course, in our prediction, we did not account for the volumetric dilation of the ultrasonic receiver. Okay, so this is the particular chicken breast, and this is actually the image that we get. And that is somehow what we expected. We expect to see the boundaries, because those are the ones who go with the bigger volumetric dilation. And this is the reconstruction we did when we moved the linear ultrasounds in the cross direction. Let me show you now. We were saying, okay, good. We know that an organic material, highly saturated, high conductivity, is going to produce strong responses. But now what happens when you go and start to see, can we actually produce volumetric dilation in rocks? And so what we did is we put here the rock, okay? Here is the linear transducer, and here's the top view, and the waveguide is radiating the rock, and that is going to go through volumetric dilation, and most of the sources are going to go from the front and from the back, and are going to arrive to this ultrasonic receiver. And if you look at the signal, once again, this is somehow like the volumetric dilation of this background, but this is the response of the sandstone. And if you remember the shape of the sandstone, it was curved on the front and it was flatter on the back. So we were very happy to see those results, and actually to see the thermoacoustic signal from the rock. So now what we were thinking is, okay, what happened when you start simulating some porous media? And once again, we have the waveguide that is radiating the energy, and what we have is that is an oil tank, and this is the sand bottle, and we have the different porous media that is defined as, let me see. So right now we have a sand particle, we have a little water there, and then the rest is air. So this is actually air. So if you look at what happened in terms of the position of the temperature in that particular porous media, actually there is a strong signal in this particular region and strong temporal deposition there, which depends on the excitation of the electromagnetic wave. Now if you look at the strain, is interesting behavior. It seems like there is a larger strain on those particular areas that are not close to the water layer. So I hypothesize that that's because of the heat capacity that you can have here with the water versus the one with the air. So actually it's growing in that direction. You can see a little bit more also on the stress, but still, as you can see, there are not very large amounts. And this is the acoustic pressure that you will be producing in that particular media. So we actually compute what are the different fields that you can observe in different positions, and you can see that this particular shape variation. So we did some interesting experiments that, I was not going to include them, but I decided to do it because it's interesting to see that. What we did is, so we have a bucket with the dry sand, and what we did is we inject some water. So here we use a syringe to inject some water in that sand. And what we wanted to see is, so what happened to the thermoacoustic signal as long as you start invading what is that area with different levels of water saturation. And so we start with some dry sand, and we end up with some wet sand. And once again, we have the transducer located on the side. So if you look at the thermoacoustic signal, and I'm sorry because, and that's why I have doubts about showing these results, because we don't have actually ground truth to compare. But what I want to show you is that when we start injecting the water, the amplitude of the thermoacoustic signal start to grow and start to variate. So we are very excited to see this behavior and the complex interaction that we get in that particular area, because we think that this could be potentially a good way to be able to do the imaging all across the porous media, and we could be potentially doing it in 3D and relatively fast. So that's what we want to do next. And I'm way too long, but just let you know, just very quickly, this is the fusion of the electromagnetic with the acoustics by trying to reconstruct the petrophysical properties for different levels of saturation. And I don't want to take any more of your time. The idea is that our algorithm converge well to fuse both electromagnetic and acoustics for sparse variations and so on. So in summary, we have modeled these thermoelastic wave analyses, doing the imaging, applying distributed optimization with ADMM that enable norm 1 or 2 regularizers. We have used information theory to maximize information transfer efficiency from imaging and observation domain. And now we want to use actually thermoelastic Green's functions in order to do the imaging, and also not only do the imaging with the electromagnetic and acoustics, but also with the thermoacoustics in the same way as I mentioned before on the petrophysical domain. And that's it. Back into the topic.
Let's first